Good morning everybody. So, we are back with fluorescence spectroscopy again. So, in our last lecture we have discussed this Marcus theory of electron transfer. Various aspects we tried to understand. In this lecture, we will continue with this electron transfer. So, just for a brief recapitulation, now in Marcus theory, three important events are electron transfer, molecular reorientation, that is the molecules which are involved in electron transfer, these are reoriented, and then third one is solvent reorientation. These are the different important steps in electron transfer process. Now, this electron transfer rate, that several factors are important, like this classical, this Arrhenius expression, that it has some constant times exponential to the power some energy factor. So, these are similar to that, it is also having that expression, and rate of electron transfer, it is related to three factors. One is this KELR is actually electron transfer rate, although this two symbols have been somehow equalized. So, this is electron transfer rate. So, this R should not be there. So, electron transfer rate KEL, that is equal to nu n R, then KEL R, this is your electron transfer, okay. Then KNR, okay. So, actually this is a typo, that it should be should not be like this, it should not be this R, okay. So, this one is your nuclear vibration frequency, this one is the electronic transmission factor, and this is your nuclear factor. And we have tried to explain various situation, that is inverted, optimum and normal region, and these are the different parameters, okay, parameters that are important, okay. So, basically, and if you want to read more, you can go through this one. Now, here actually this donor and acceptor, they are separated by a spacer, and this is your D star A, and this is after electron transfer has taken place, okay. And as I told you, reorganization energy is the energy needed to distort the product state and its surrounding to reach the equilibrium configuration of the reactant state. And when the barrier is known and the electronic coupling is weak, then you need to apply the non-adiabatic expression as below, where this electronic coupling matrix is V, and this has got a very similarity with the Arrhenius expression as this, and this pre-exponential factor, that is like A is the pre-exponential factor, and here for non-adiabatic cases, if the coupling matrix is smaller than the thermal energy kBT at room temperature, then B is in general diminishes exponentially with distance, and also distance dependent electron transfer rate can be described by this Kcs equal to k0 into exponential minus beta Re. Now, beta is the attenuation factor, it is scaling the distance dependence, and Re is the edge to edge distance. You have the donor, you have the acceptor, then this edge to edge distance is Re, and there are several conditions for Re, like if they are separated in vacuum, then you have some range of value of beta. In case of protein, you have got some beta value. In case of solvent like benzene, you have some beta value. So, using different beta values, you can calculate this rate of electron transfer. Okay. Okay. Now, next is if the donor acceptor are linked by saturated hydrocarbon, then it is a through sigma bond interaction. So, through sigma bond interaction means in that case beta is rather strong, okay, and for hypothetical graphite bridge, okay, then interaction will be so strong, it will be so strong, there your charge transfer, okay, charge separation and recombination will be vibrationally limited. I mean it is a very fast process, I mean close to the vibrational frequency limited. I mean in that case beta is equal to 0, okay, and if the energy level of the bridge becomes too low, it can work as a trap for the electron. So, electron will be transfer will be stopped and it will remain trapped at some point in the bridge or in the spacer. The through bond interaction between D and A is is an interaction between the electronic orbital of D and A. So, it is basically electronic orbital interaction, okay, and the orbitals of the linker. I mean linker means orbitals involved in the linker over here. So, if it is a through bond, so all these sigma bonds or these sigma pi electrons are taking part in the interaction. Okay. Now, the question is how this electron is transferred, okay, how this electron is transferred in a system consisting of a donor and acceptor pair connected by a spacer or connected by a linker, okay, or connected by a bridge in which D has the, suppose D has the lowest excitation energy, and you can visualize in the figure that I am going to show. So, you see here you have got donor, spacer and acceptor, okay, excitation, that is you put H nu, then D star S A, and you have got this charge separated state as D plus dot S A minus dot, and these are the respective numbers over here, that is delta G double dagger and the delta G 0, okay. So, these are the respective numbers, and this is your nuclear and solvent coordinate, okay. Now, here we have designated 3 points, 1, 2 and 3. We have designated this 3 point, I mean 3 situation, as if the electron is localized, I mean localized in point 1, I mean first denoted by 1, then denoted by 2 and then denoted by 3. So, it is a transmission of electron from this region to the other region, okay. So, So, what is happening? I mean, so we would just like to understand what is happening over here. Okay. So electron is transferred this way from here to here. So, electron transmission from this, this reactant to the product surface. Okay. So, now all these things are already stated. So, what is happening that upon excitation of D, one gets D star and D star SA, okay, and the electron is promoted from a low lying state to a state. I mean, low lying state means it is a state where, I mean, from a low lying state, you see over here, you just from a low lying state, I mean from here to here. Okay. As electronic coupling is present, a very small chance of finding the electron on the acceptor side. So, you see that if I look into this diagram, you see that it is the spacer, it is your donor, it is the acceptor, and this is the delta E after H nu. Okay, when you put H nu, then it is excited, and then it will move to this, maybe via vibration or relaxation or something, so that it can reach this region. Okay, that is so that it can cross the barrier. So, barrier is over here. So, it will, I mean, as if you put a ball, so it will move this way, and then it will reach this, and it will reach this now number 2 point, I mean the point where it is denoted by 2, and then it has got the equal probability of coming back to here or going to this side. Okay. So, that is why, so basically it is the relaxation, I mean what I told you, that this relaxation, that is because of the vibrational relaxation. So, you are getting these things. Okay. So, you are getting those things. Now, the point is that okay. Now, number 2, after reaching the barrier, what is happening? Okay. After reaching the barrier, it has got the equal probability. It has got the equal probability either to go to the product state or come back to the reactant state. Okay. So, let us again see the picture. Okay. So, ball is over here. Okay. So, it will either come back to here or it will go to there. So, in that case, your delta E was not equal to 0 over here. Now, delta E is equal to 0, because it is over here, it does not require any barrier, because it has already crossed this barrier. So, it is over here, that is why it is delta E is equal to 0. Okay. And then it has got the equal probability either to this side or that side, and see that initially your probability of finding the electron, it is more localized into reactant surface. Okay. It is more localized to the reactant surface than the product surface. So, that is why its probability has been shown to be more than this one. Okay. So, that is why it is given, I mean denoted with a smaller sized ball, and it is a bigger sized ball. That is just to show you that probability of finding the electron which is going to be transferred is more in this reactant surface. Okay. Then it reaches over here, so that you get this almost, I mean equal probability distribution. So, it has got the equal probability to move to this side or that side. Its delta E is equal to 0. Next, what is happening, that after crossing the barrier, it is going from the top to the bottom of the potential energy well of the product state, and leads to the mixing coefficient evolution and a reduction of electron probability density on the donor side, and an increase in electron probability density on the acceptor side. So, what is happening, that you see initially the mixing coefficient, if you think of, so mixing coefficient of this donor state and the acceptor state, or the reactant state and the product state. So, it is dominated by the reactant state and contribution of the product state is very small. So, here almost equal probability. So, they are contributing almost equally when it is over here, and then here you see that this contribution of this reactant and product, if you think in that way, then you will be finding that you see it is more on acceptor side rather than in donor side. So, that means there is evolution of this coefficient, okay, evolution of the coefficient, and so that it evolves from reactant to the product surface, and now delta E is huge, you see. So, in order to go back, that means in order to get the reverse electron transfer, okay, you need to have you need to be transferred from here to here, okay, because it is an electron transfer. So, that is why you have to have a vertical line connecting your product surface and the reactant surface. So, that means unless you supply this much of energy, you will not be able to reach to this. Like here you see, if you start from here, then this much of energy is required to go to directly to the product surface. Okay, that means you should, if you get a promotion like this from here to here, maybe some electronic excitation, then directly you can switch to this vibrational level, and then you can be transferred to here. Okay. So, here you require this much of delta E to be passed from product to reactant. Okay. So, that means in that case an enormous amount of energy requirement is there to come back to this state. So, it is a reverse electron transfer energy requirement. Okay. So, during these events, okay, whatever events I have stated, that is by 1, 2 and 3, that means it is you have your like this one surface, another say surface like this, then it is your excitation, then it will go this way. Okay. This is your 1, this is your 2 transition state, and this is your 3 product state, reactant state, and this is your product state. So, it will go this way, and then ultimately it will reach over here, and then it has got the equal probability to be in this side or to be in the other side. So, it will go this way, and then ultimately it will reach to 3. Okay. So, energy difference between the initial and final state with respect to certain nuclear coordinate. Why certain nuclear coordinate we are talking about? Because there is an electronic transition. Whenever there is electron transfer, it is electron redistribution. So, electron redistribution means it takes very less time. So, during that electron redistribution, I mean that electron redistribution process occurs in a static framework provided by the static nuclei, as if during that time, during that period, I mean maybe your nuclear coordinate is fixed. That is why with respect to certain nuclear coordinate we are considering. Okay. So, energy difference between the initial and the final state with respect to certain nuclear coordinate, it changes sharply. So, initially it was like this much, then it is 0, and then again it is very high. Okay. So, like this. Here it is like this much. So, it changes sharply. Okay. So, what is happening that here it is your delta E, this is your delta E prime, and this is equal to 0, here it is 0. Okay. So, while going to the top, the barrier delta E decreases and become 0, because there is no barrier this way or that way, because it is already on top of this hill. Okay. Now, at the top, the mixing between two states is strongest, so that you have like a dumbbell kind of donor acceptor, I mean electron distribution, almost equal probability. Okay. I mean if you plot this way, it looks like this. Here it is, this is for the midpoint, here it is like bigger over here and smaller over here, and the probability distribution is something like this. Okay, this is donor, mostly on donor, less on acceptor. Here in this side smaller and this side bigger. Okay, this is donor, this is acceptor. Okay, so electron has been transferred, I mean through this barrier to over here. Now, entering into D plus dot S A minus potential surface. So, this is a product, means D plus dot spacer A minus dot. This spacer may be like hydrocarbon spacer or maybe something else as well. The moment it enters into this surface, this gap increases again like this. Electron transfer rate can thus be viewed as the time taken by the wave function. Okay. So, you see that it starts from here, then goes to here, then to here. Okay. So, this may be viewed as the time taken by the wave function or the time dependent Schrodinger equation to evolve from one 0 order state to another 0 order state. 0 order state means in which it is described primarily as if there is no mixing between this state, donor state, and the acceptor state, because the electron is primarily localized on D, and here the electron is primarily localized on A, but here it is intermediate between these two. So, that is why it is a mixture of this and that. So, it is the time required to have this 0 order state to evolve to another 0 order state through this intermediate state. Okay. And this time, I mean the time required to get this becomes longer if electronic coupling between the two states become weaker. I mean if electronic coupling is not high, then it happens, but it happens slowly. Okay. Next, some important point that we should look into, that basically in this electron transfer process, okay, after the Frank-Condon excitation of the donor acceptor system has occurred, there is a vibrational, I mean in case of any electron transfer, if you think of, okay, that you have one well, say there is another. So, transition will take place in such a way that it is over here. So, it will try to get a place where it receives, I mean it has got vibrational probability distribution more. So, in electron transfer process that occurs after Frank-Condon excitation of a donor acceptor system, the direct overlap of the vibrational wave function of the initial and the final state plays a very important role. So, basically just think of this diagram. Okay. So, in this region you see that maybe here if I have got this, okay, like this, okay, this side energy and this side R. So, in this region there is some kind of overlap, because it may be thought to be extended outward also a little bit. So, there is overlap, okay, and that overlap helps the transition, I mean from this state, I mean reactant state to the product state. Okay. So, this overlap is direct overlap plays a very important role, and you know what is happening, that this electron transfer, it is described as, you know, described as the nuclear tunneling is related to this, basically this overlap. Okay. So, as if this vibration has been, I mean this vibration has been transferred from this side to this side, and if we want to if we want to understand the influence of Frank-Condon factors in relation to the Marcus theory, then we should include, I mean we should consider Marcus theory, we should consider the Marcus theory from the point of view of this quantum mechanical this tunneling. Okay. And also this inverted region, I mean this Marcus inverted region can be well described in terms of this in terms of the nuclear tunneling phenomena, I mean which we cannot explain with the help of this classical theory. Okay. Classical thermodynamics, that if we increase this driving force, that tends to increase your rate. That does not really happen. Now, in case of your normal normal, if we just plot some vibrational ladder, if it is a normal case, then it may look like, so this is one potential surface, that is another say potential surface, then we can just think of having some overlap, like say and maybe it is over here. So, okay, so there is a good amount of overlap over here, it is for this normal. Okay, so vibrational function overlap. So, that is a nuclear tunneling. Then if it is an optimal one, then optimal means you have this surface, you have another surface like this, and maybe you have this one, and say you have in this region, so let us draw it in black, so that say something like that. So, you see it is maximum overlap over here, here overlap is less, and if it is inverted, if it is inverted something like this, say, so you have this okay, and say this is your inverted case. So, you have like then like this, another over here, maybe another over here. So, maybe for this one, maybe you can write like this, and for the whole one, bigger one, you can have like okay. So that again there is a small, very small overlap region over here. So, so there is a thin barrier, you see, means all these cases, if you think of, there is a thin barrier to the product set when viewed in a classical way, okay, because there is a very small barrier, this is your, okay, let me draw with a black pen so that you should be able to understand. Okay, so barrier should not be high, if you think classically, but if you think of this vibrational wave function, then we could see that because of the barrier is thin, the overlap of this wave function is larger than the expected on the basis of the barrier height. So, this may change, I mean, all the barrier is thin, but this overlap it may change depending on their placement, and therefore, depending on this placement and their overlap, your rate of this tunneling from one surface to the other may get affected. Okay. Anyway, so so that completes the discussion with respect to this Marcus theory. So, next we will move on to another topic which is called, it is also related to electron transfer process and that is called exciplex. Exciplex. So, exciplex is again an example where the electron transfer is taking place in the excited state. So, classic example means we have been discussing this Marcus theory. So, you have your ground surface, this is your excited surface, and there is another this is your reactant surface and this is your product surface, and electron transfer is taking place, and as a result of which from reactant to product there is a transition, so that you get d star A to d plus dot A minus dot, this one you get. Okay. So, it is an excited state, basically complexation, we heard about complexation. Okay. And this is an excited state complexation. Complexation in the excited state. That means nothing is happening in the ground state. So, think of this electron transfer process, that suppose you have got your HOMO and LUMO and you have this electron. If you have an acceptor over here like this, then one electron may be transferred to here. Suppose acceptor ground state is this, so that this acceptor is reduced. But if the situation is such that its disposition is different, say over here, then this process not possible, because it is an energy demanding process. So in that case what to do? So in that case the best thing is to, as I explained to you, that if you can excite this over here so that it comes over here, then it can be transferred to here, giving rise to this donor plus dot and acceptor minus dot, and this happens only in the excited. So you see that when electron is transferred from one species to another, so there is a donor, there is an acceptor, electron is transferred, means this becomes, say if it is a donor, if this is an acceptor, then this becomes plus charge and this becomes minus charge. So what is happening? That means if this is plus, this is minus, then there is a Coulombic interaction. So if Coulombic interaction is there, then they will come close to each other. And then if they come close to each other, if you recall our earlier lecture, then this charge separated charge transfer state, okay, this charge transfer state, this will have possibility, like if it is a charge transfer state, it may do non-radiative excitation to the ground state, or maybe it can emit H nu CT. Okay. So, depending on the external factors, external environment, depending on the external environment, what we can do is we can have H nu CT or we can have no H nu CT, that is charge transfer state may not emit. Okay. So, that is why, I mean, solvent has got enough importance with respect to such electron transfer process or charge transfer process in the excited state. So, it is a complex session. Why it is a complex session? Because after the charge transfer has taken place, so one species become, say, M becomes M plus, and the one which has accepted electron becomes A minus. So, there is some interaction leading to a complex. Okay. But in the ground state means if it comes back to the ground state by back electron transfer or by some mechanism, there is no interaction. So, if you do not excite M to M star, you do not get any type of such thing. Okay. So, exciplex, it is excimar or exciplex, whatever you say, that excimar formation is a special case of general class of weakly bound complexes and excited state molecules and ground state molecule. Actually, exciplex is similar to this term excimar. It is a heterodimer, basically heteroeximar. Exciplex is heteroeximar. When one monomer and another species, they are interacting, then you can get exciplex. It is generally a charge transfer complex, CT complex generally, although in case of homo dimer or which is called your excimar, this is called heteroeximar. So, in case of excimar, what you have M star and you have M, then they will form some weak interaction complex in the excited state, although in the ground state nothing is happening. Okay. So, these are all weakly bound complexes. So, characteristics will be weakly bound complexes, and depending on the extent of, if it is an electron transfer or like that, then depending on the extent of electron transfer, it may be sensitive to solvent or it may not be sensitive to solvent. Okay. So, for excimar homodimer, identical same molecule in a pair of which one is excited, another is not excited. Now, However, this pair need not be identical, and when it is not identical, these are called heteroexcimer or heterodimer. And in 1961, Wheeler and Leonhard observed that fluorescence spectrum of biphenyl in cyclohexane. Biphenyl in cyclohexane in absence and in presence of diethyl aniline. Biphenyl is this, in presence of diethyl NET2. Okay. And in addition to this normal fluorescence, they have observed an additional band in the red side of the spectrum. So, fluorescence spectra, and this is wavelength. Then if it is your normal spectra, say for example, then in presence of this, you see that this is reducing in intensity and additional band is created, additional band is formed, and this is called your exciplex. And generally this exciplex is having, you see your starting emission was with structure, and this exciplex emission, okay, is generally structureless, or even excimer emission is also structureless. So, these are the characteristics, and these band, this broad band, broad emission band, and it is a red shifted broad emission band. It is structureless, and in some time it is found to be very much sensitive to solvent. Okay. Why sometime? Because especially for exciplexes, it is very much sensitive to solvent. Okay. So, this is a characteristic spectra of the compound, that suppose if this is your emission spectra, it is progressively reduced and an additional band is there in the red side of the spectrum. Okay. So, red side of the spectrum, and if we increase the polarity, several factors that are responsible. So, maybe polarity of the medium, if you increase the temperature, okay, then if you de-aerate the solution, there may be some effect. So, there are several factors that are responsible for their with respect to the facility to formation of this. Okay. Now, typical example will be like if you have a pyrene, okay, plus say dimethyl aniline or diethyl aniline, okay, in say benzene or maybe in ethanol or maybe other solvent, you may expect to have, especially in benzene, you will be getting a good exciplex emission. Okay, good exciplex emission you will be seeing. Okay, so pyrene is a classic example of this. You see that pyrene structured emission, okay, and if you add say something like dimethyl aniline or diethyl aniline, you will be finding this broad emission in the red side, and this is also broad, but with increase of polarity it is shifted towards right, maybe with a little diminution in the intensity of emission. So, its characteristic is it is a broad emission spectra, and when there is an electron transfer, that is the idea is that you have pyrene in the excited state, although there is no ground state interaction between this molecule, this dimethyl aniline or diethyl aniline with pyrene. So, gradually when you add this diethyl aniline or dimethyl aniline, then, and of course, you should de-aerate the, you should degas this solution, because oxygen will create trouble, especially oxygen is a triplet quencher. Sometime in presence of oxygen, complication may arise, which I am not going to describe or discuss right now, but what I just want to mention is that it is an observation that you will get broad red shifted emission, which is sensitive to polarity, is called the exciplex emission, and this exciplex is also a class of weakly bound complexes. This is formed in the not in the ground state, but in the excited state is formed. Okay. This is a class of compound, I mean weakly bound system. Okay. It is not a true chemical linkage. It is not a true chemical linkage, but it is a type of weak interaction between the pyrene, weak interaction as a result of this electron transfer from excited pyrene, because in the excited state, as I told you in earlier lecture, that if you increase, if you excite say some system, then its redox potential or reduction ability or reducing ability is altered. So, in the same way, if you mix pyrene with DMA means without the presence of light or in absence of light, nothing is happening. If you take the absorbance spectra, you do not see any new band. Okay. But the moment you use the excited pyrene, then additional band is coming, which is solvent sensitive, and generally its lifetime is in the order of several nanoseconds. And this exciplex, its behavior, its dynamics is interesting, that we will discuss exciplex in details in another class, but this exciplex has got importance, in many application with respect to technological progress, that this exciplex fluorescence imaging is a technique that if you have say something like, say you have got a plate or you have got a cell, living cell or maybe some say plant cell or whatever, that you put some dye, so that the whole cell is now having dye molecules. Okay. Okay, then you shine with radiation and you take the image of the emitted light, okay, with the help of some special device which is called the microscope, fluorescence microscope. Okay, so that you can cut off this special device means you can cut off your excitation source, and depending on the interaction in the various region of a cell, you can even enlarge the with the help of a microscope you can view a cell, very small cell in a bigger a bigger picture you can have. So, you can get the image, of the cell, and depending on the interaction of this dye molecule, or if the dye molecule is a reporter of certain type of environment, you can get information of various parts of the cell. Okay. In some cases maybe you will be observing that it is quenching of luminescence of your dye, or maybe in some cases in some region you will be finding it has enhanced. In some cases in some region you will be finding something else, some other interesting observation. So, exciplex fluorescence, since it is a red shifted broad emission like this. So, by monitoring the exciplex fluorescence, you can by monitoring the exciplex fluorescence you can get information about like say fuels. Okay, think of an engine where this in a combustion chamber, the fuel is taken inside and then it is compressed and then maybe it is burnt. Okay, before its combustion, what is the fate of that fuel? The point is that exciplex is formed when your fluorescent molecule and your quencher comes in close proximity, and that is only possible if you have vapor phase. I mean, if you have small droplets of liquid phase in the form of small droplets, so that in those small droplets your fluorophore and your quencher are in close proximity, and it will give you emission. And where only vapor phase is present, maybe you can expect to have only this blue emission. Okay. So, by this information, I mean by monitoring this blue emission or monitoring this green emission, you can in principle find out the distribution of your this fuel inside the chamber, means how it is distributed inside the chamber. So, that is an advantage. So, exciplex fluorescence imaging, using this exciplex fluorescence imaging, you can in principle look into the into this type of distribution process. I mean how it is distributed inside that chamber. And also, if you have if you want to study the interaction of maybe two species, of which one is having your fluorophore, another is having your quencher, then if they come close to each other, then there is a chance of transfer of this quencher. Okay. In close proximity of your quencher, means say DMA, in close proximity of your pyrene, and then and only then you can have exciplex emission. So these are the aspects that I am going to take up in the next class. So what we have learned in this particular lecture, that we still have been dealing with this Marcus theory of electron transfer, and how this electron is transferred, and the Frank-Condon overlap between the product state and this reactant state, how that affects your inverted region or this normal region or this optimal region, that we have discussed. And we have started with this exciplex, that is exciplex is a result of electron transfer in the excited state, and with a coupled quenching of luminescence of your fluorescent molecule. And we have just given the example of pyrene and several other, like pyrene and maybe anthracene DMA, pyrene DMA. We have just started with that. And in the next lecture, we will take up the dynamics of this exciplex formation and several issues. So till then, have a nice time. Thank you.